In today's lesson, we're going to be working with radicals. So we'd like to focus our attention on questions of this type where you're given a series of radicals, either adding, subtracting, multiplying, and we're expected to expand and simplify certain expressions that involve radicals. Let's take a look at a bunch of examples on how you work with radicals. For our first expression here, we have 3 root 20 plus root 45. We need to break up this radical here. And the idea here is you want to think of the largest perfect square that lives inside of each one of these. So for instance, if you take the number 20, I can factor that as 4 times 5, and this is a perfect square. So if I go to evaluate the root of 20, that breaks up into the root of 4 times 5. But your root function, in case you've forgotten, your root function in general, if someone gives you the root of x, that's expressed as x to the power of a half. So it shares the same property that exponents share. So in this case here, the root of 20, I can actually break up into the root of 4 times the root of 5. Again, that's just using our exponent rules. And then from here, this reduces to become 2 root 5. So that's generally what we want to do here is given some radicals, we want to break it up into an expression where you take out any of the perfect squares, you can take those out of your radical. So I can replace the root of 20 in this case with 2 root 5. Similarly, we can do the same thing for the root of 45. If you look at the root of 45 here, the root of 45 is going to break up into the root of 9 times 5. And again, 9 is a perfect square, so that'll break up into the root of 9 times the root of 5, which will be 3 root 5. So now we have the root of 20 can be expressed as 2 root 5, and the root of 45 can be expressed as 3 root 5. I can now sub this into our equations, giving us the following. Now you'll see here I replaced the root of 20 with 2 root 5 and the root of 45 with 3 root 5. Now we can multiply the coefficients here together, giving us 6 root 5 plus 3 root 5. Now in this situation here, you can think of the root of 5 here as a variable x, and we're essentially collecting like terms here. So I have 6 of these root 5s, and I am adding another 3 of these root 5s. So in total, we will have 9 of these root 5s. And that is our first example. And for the next example here, we want to go ahead and reduce each of these radicals. So I want to take the root 18, the root 50, and the root 98. I want to be able to break this up. So let's tackle each of these separately. All right, so I went ahead, I took a look at the root of 18. I broke that up into 9 times 2. And the root of 9 is 3, and then your root 2 is left alone like this. Same with the root of 50. I broke that up into 25 times 2. That was the largest perfect square I could think of, and that becomes 5 root 2. So if we take a look here, what is 98? How can I break that up? Well, if you're not sure of the largest number that it decomposes into, we can first see that it's divisible by 2. I can break this up into 2 times 49, and then right away, hopefully you see this here, 49 is a perfect square. So therefore, what I can do is I can express the root of 98. I can break that up into the root of 49 times 2, and that 49 will pop out and become 7 root 2. So now let's go ahead and substitute in these values here for our roots and simplify. All right, I went ahead and I replaced the root of 18 with 3 root 2, the root of 50 with 5 root 2, and the root of 98 with 7 root 2. Now I'm going to go ahead and multiply these coefficients together and simplify, giving us. So going ahead and simplifying here, I end up getting 6 root 2 minus 25 root 2 plus 21 root 2. Again, these are all like terms. We have 6 of these. We're taking away 25 of these root 2's and then adding another 21 of these root 2's. So in total, we have 2 of the root 2's. So our simplified answer becomes 2 root 2. Let's look at another example. In the next example here, we're asked to simplify 8. Now this is the third root. So in general, if someone were to write the square root of x, implicitly this is referencing the second root. And what you're doing here is when someone asks you for the square root of x, it's what number do you multiply by itself twice to get x. If you're asked to evaluate the third root of 216, what you want is you want to find the value of x such that you multiply by itself 3 times to get 216. So going through these values here, you'll find that 6 cubed, i.e. 6 times 6 times 6 is 216. So this expression will break up into 8 times 6, which gives us 48. And that is our simplified expression. Let's look at another example. In the next example here, same idea, we want to simplify the following expression. So if I write this back in exponent form, I would work with the innermost bracket first, and then we can worry about the other square root afterwards. So in this case here, we have our 8 to the 4th, we are taking the square root of this, so in which case this will be to the power of a half, and then we're taking the square root a second time, so that will be to the power of a half again. So now we're in a situation where we have a to the power of 4 to the power of a half to the power of a half. And you remember from your exponential work that this is power to a power to a power. And whenever you raise power to a power, you just multiply those exponents together. So in this case here, this will be a to the power of 1, as 4 times a half is equal to 1. So simplifying this, you can just write it as a, and implicitly that is meant to be a power of 1. Let's take a look at another example. So in the next example here, again, we want to expand and simplify this. Now we're multiplying two binomials, both of which involve radicals. When you're doing that, you want to go ahead and do your FOIL method. So we're going to multiply these together and multiply these together, expand that all out. So let's go ahead and do that. Doing so, we get, all right, so I went ahead and expanded this using FOIL. I did not go ahead and multiply these together as soon as I distribute. A lot of times people will do that. I thought I'd show it explicitly this time, but if you notice here, putting these together here, what do we get? When you multiply the coefficients together, that's going to result in a 10. Now, what happens when we multiply the root of 2 times the root of 2? When you multiply the root of 2 times the root of 2, you're using your exponent properties in reverse. So in this case here, the root of 2 times the root of 2, you can put that together as the root of 2 times 2, which is the root of 4, which is 2. So this simplifies to just becoming a 2. For the next expression here, the coefficient number in front of this root sign is a 1. So this will be 5 times 1, which is just 5. Now here I have the root of 2 times the root of 3. Again, that just goes all under the same root sign as root 6. And we move on to our next expression. This will be 2 times 2, which, as we know, that's going to be positive 4. And then now we're taking the root of 3 times the root of 2. And again, that goes under your root sign and gives you a 6 again. And now we have here 2 times 1. 2 times 1 is 2. And again, that'll be the root of 3 times the root of 3 this time. And you'll notice if you take the root of 3 times the root of 3, and you'll notice here, if I do take the root of 3 and multiply that by the root of 3, again, you can put that under the brackets. That becomes 3 times 3, which is the root of 9, which is 3. So I can change the root of 3 times the root of 3 to just become a 3. So now that we have all this, I can go ahead and collect like terms. You'll notice here, this gives me a 20, and this gives me a 6. So 20 plus 6 is 26. And now we're in the same situation here. I have minus 5 of these root 6's, and I'm adding 4 of these root 6's. So in total, I have minus 1 of these root 6's. So my simplified expression becomes 26 minus the root of 6. Let's take a look at another example. So for the next example, here, same idea. We want to use our exponent rules. Let's rewrite this one here. I've got the square root of a cubed. Rewriting that in exponential form, that would be a cubed to the power of a half. Minus, now I'm taking the square root of a to the power of 5. So that's a to the power of 5 to the power of a half. In which case here we get a times a to the 3 halves. Minus a times a to the 5 halves. So now if you take a look here with an expression like this, I'm multiplying two exponents with the same base, i.e. the base here is a. The exponent on this a value is actually a 1, it's just not written, so I can go ahead and put a 1 on both of these here. So whenever you multiply with the same base, you add the exponents. So in this case here, I'm going to add the 1 and 3 halves together, giving us 5 halves. So this will be a to the power of 5 halves. Minus, here it'll be a, and again we add these exponents, this will be a to the power of 7 halves. And now in this situation here, we are fully simplified. There's nothing more I can do here. These cannot be subtracted. They're of different powers, so they're no longer like terms. So this is our final answer. Let's take a look at another example. So in our final example here, we're asked to expand and simplify the following expression. When you're in a situation where you're asked to expand out a trinomial, and this is to the power of 2, the general technique is to group two of these together. So for instance, I'm going to group together the root 3 and root 5. I could have easily grouped together the root 5 and root 2, or even the root 3 and root 2 together. But I'm going to just arbitrarily, I'm going to grab together the root 3 and root 5. So when you expand out this binomial, you're going to square the first term, which now I'm treating this as one term. and this is my second term. So you square your first term, to which you get root of 3 plus the root of 5 squared. Then it's going to be the first term, which is this, times the second term times 2. So that'll be 2 times the root of 3 plus the root of 5 times the root of 2. And lastly, we square our last term. So in this case here, we're going to square the root of 2. So now that I have this here, we're going to tackle each of these three problems separately. So let's focus our attention on first expanding and simplifying this. So if I do this here, we're going to square the first term. So that's going to be the root of 3 squared. First times second times 2, that's going to give me 2 root 15. Again, 3 times 5 is 15. That all goes under the root. Plus we square our last term, which is the root of 5 squared. Continue. I want to expand out the following expression. Before we do that, let's go ahead. I'm going to put the 2 and the root 2 together. I'm going to go ahead and simplify the following three terms quite easily. You'll see each of these, the root of 3 squared is 3, the root of 5 squared is 5, and the root of 2 squared is 2. So I can go ahead and write these out here. I'm going to also distribute this expression into the binomial, giving us the following. So you'll see here I went ahead and simplified those expressions. When I distribute this into the binomial here, this became root of 2 root 6 and 2 root 10. Now we can go ahead and collect like terms, like add my constant values together. Doing so gives us 10 plus 2 root 15 plus 2 root 6 plus 2 root 10. And you'll notice there's nothing more that we can do here. I can't put these together. These are not like terms. I also do not have any perfect squares that I can factor out of these. You'll notice 15 is 3 times 5, this is 3 times 2, and this is 5 times 2. So there's no more further simplification that can occur. So our final simplified expression is as follows. That concludes today's lesson on working with radicals. Thank you.